Yeah, you.
Yeah, so I'll share my screen. Is my screen visible? Confirm that. Oh, no, not
Not
yet.
yet.
Yeah, and now,
Yeah.
so this is the fourth dimension. And yeah, now it's visible, I guess. So, recurrent neural networks, welcome to today's session. Thank you for taking out time in your weekends to join this. So these are our main topics today. What are neural networks? How do neural networks work? Why do we need RNNs in the first place? And what's wrong with RNNs? And then what are LSTMs and their applications? I promise very less math or low to no math because that might scare you people just like it scares me. So this is the perceptron historical biomimicry, as we call it, because what these scientists have decided was to investigate how our brain thinks. So in order to do that, they were just trying to go from outside to inside, and in that process, the least they could go to was a perceptron. So our brain has a lot of neural pathways which provide electrical impulses to store information. Nobody knows how a perceptron works from the inside or how a neuron works from the inside. But that was the closest point that scientists could come up. And what they did was simply mimic it in our computer world. So that is how give birth to a perceptron. So what is perceptron? It's simply the smallest neural network that you can see, and it simply takes the input, adds or multiplies it with a weight, adds some bias, and puts it into a step function or an activation function, and then gives you the output. So that's all happening there. And even the math that you or people are really afraid about, it's just multiplication, subtraction, and addition, and maxing. That's it, in just in matrices. So a simple neural network. To understand what a simple neural network is, I thought of developing these mnemonics, and then I'll be also sharing those with you guys. A kid is only happy when he gets what he expects. So probably a gift that he wants, and he already has an answer in his mind on what gift he should accept. So unless and until you give that gift to him, he's not happy. And the layers, the perceptrons are replaced by the bodybuilders because weights is associated with bodybuilders. That was very bad, but I couldn't come up with anything better. So generally, what these bodybuilders do is take the box, add their weights, and do the magical computation, activation function, and stuff, and give it to the kid. Because we already know what the kid expected, we as in the kid knows what he expected. So he shows his expression of satisfaction. If he's happy, he'll smile. If he's not happy, he'll not smile, he'll cry probably. So your goal is to make the kid happy and learn how to make the kid happy again and again. So what you can do probably is change the weights and try out a different orientation of weights and try out a different combination of weights. So that is all happening in a neural network under the hood. So it's all a bunch of weight adjustments to make the kid happy, or else to reduce the loss. Loss is nothing but if the kid is unhappy, that's loss, and you want to reduce it to zero. Problem. Ideally, you want to reduce it to zero. Ideally, it cannot be reduced to zero. So yeah, practically, it cannot be reduced to zero. So that is the goal of all these layers, and this can be visualized as a bodybuilder whose only motto of life is to make this kid happy, no matter what. And what is backpropagation? Backpropagation is the process of learning in the neural network. So when the kid is unhappy, the gift box backpropagates. So the kid throws it probably to this bodybuilders, and then they try to figure out what's wrong in this box. So these bodyguards, there might be many layers in a neural network. This was just a simple neural network. Level 1, level 2, level 3, level 4. The goal of all these bodyguards is simple, just make the kid happy. Now level in this case, if this bodyguard's only goal is to make this kid happy, and he only knows to adjust his own weights, so he's not bothered about what weights were previously added and what weights will be added in the next layer. So he will only adjust his weights, and likewise every layer's bodyguard is only concerned about his own weights contribution. He's not bothered about what the previous guy and the forward guy is thinking. And likewise it goes to the input layer till the input layer, and then again these guys try to make the kid happy. If it works, then fine. If they see this kind of thing is working, then they'll optimize on it, and then they'll do it till the kid is fully happy. So these are the layers you can imagine as the bodyguards. And what is really happening is simple. It's just partial differentiation. You are taking the loss and you're calculating the gradient. Gradient is nothing but the partial differentiation, and you're subtracting a part of gradient from the original weight, and again trying out that combination if this makes the kid happy or not. So this is an example of a proper neural network, standard neural network. Now, kid's happiness is in control of these two guys, but he can only control his weights. So he will do his best to adjust these weights to make the kid happy. And likewise, this guy doesn't know about the kid, so he will only want this guy to be happy, and he knows that will eventually make the kid happy, just like how partial differentiation works. And he will adjust these weights. So likewise, everybody's weights are adjusted, and they're optimized to make to bring down the sadness and slash loss. And yeah, this is optimization. The whole process of doing this is called optimization, and it's not very easy, though it looks very straightforward. This is the gradient plane. So all you have to do is you start somewhere here. You have to come and reach the global minimum of it. You might simply say what's there in this. I'll simply throw a stone and it will probably end up rolling here. But sadly, there's no gravity in machine learning and also deep learning. So you'll have to calculate all those things with math, and you have to come to the global minimum. And again, very basic. How do you calculate the minimum of any function? You equate its first derivative to zero. So gradient is nothing but derivative, and you want it to be zero. And that is how you do. There are a lot of different techniques that go into optimization. It's a next level research field in itself. People are trying different ways to optimize. And sadly, you might not reach the global minimum itself sometimes. You might get stuck somewhere in this big forest, and people are trying out different ways. And again, even here they are doing the same thing. They are biomimicking stuff. So because neural networks came from biomimicry, even they're trying optimization. Genetic algorithms are being used there. And why RNNs? So coming to the main topic finally, RNNs are nothing but recurrent neural networks, a different type of neural networks. So basically, what all we saw till now is literally in an abstract level how everything works in a basic neural network. You give some data, it learns the patterns of that data, and it predicts something. But the problem with this is it is very limited and restricted. It is one-to-one connection, one-to-one function as such, because you can't really go out of rules in a normal neural network. Because, for example, you can probably predict what's there in a picture, but to predict what's there in a video, you have to manually give it every frame of the video. So you are eventually doing this manual thing. And the Alexa, Siri, and all chatbots that we use, they were not given rules to keep the sentence length just this much. And if this guy speaks more than this, I'll go die. That's not happening there. They are smart enough to catch the context as well, and also let you speak as much as you want. So that is why we want RNNs and recurrent neural networks. Again, a simple analogy slash story that I thought would be appropriate. So imagine you are hosting a house party, and you post it on Instagram, inviting all your followers, and you also ask them to bring their friends if they want to, because you all want to have a good time together. And you have these dumb bodyguards to take care of you, so they are like, their whole life is a sacrifice to you, so they always are around you. Now you ask them to stand at the gates and make sure no stranger comes into the party so that he'll not spoil any mood of the room. Now these bodyguards have the list of your followers. They don't know the friends of your followers. So while allowing people, they might see your friend, direct friend, and they might allow him, but they might as well block the person who came with your friend, who is also probably invited, but these dumb bodyguards didn't figure out because they don't know. So that is the problem in a simple way with the regular neural networks. If you give it an unknown data, or if you ask it to figure out something out of the box, it won't because it's dumb. And the world sadly is all of chaos and time series data. So anything to everything is time series. Probably 1% of problems are solved by convoluted neural networks and regular neural networks. 99% of the problems are just time series problems. Stock price data, forecasting weather, self-driving car, etc., etc. Even the chatbots, and everything is time series. So that's why we need RNNs. And this is the architecture of RNNs. So just like perceptron, it is also taking some input, giving some output, but there's a little weak in the architecture. So they eat their own outputs. That is so cannibalistic of them. So basically, what happens here is this is the weight and this is the input. Now it calculates an output, but it also gives the same output to the next cell as an input. So the next cell is taking previous output as an input as well as a new input as an input. So it requires two of these to calculate the new output. And then this new output is again being given to the next recurrent network cell, and the same thing happens. So basically it's not dumb because it's not just relying on present data, but it is also relying on the past. So it has been maintaining the sequence from the first input. So eventually if you see, the output 2 is nothing but a series of computations which also involve output 1. So this is the classic problem. How do you predict what would the price be in some stock for say Bitcoin? What might be the price of Bitcoin tomorrow? What all do you need? Is it just enough if you know today's price? Probably not. And you probably need the history of Bitcoin prices to predict well. But you also need to make sure not give too much importance to the history, but also be aware of it. So there's a nuance in it, and nuance can only be understood by smarter people, and RNNs are smarter people. ANNs are dumb. They can't. They don't. They operate in extremes, literally. So we want nuance, and that's why we use RNNs. What does this solve now? RNNs give this memory slash context that we didn't have previously. So now bodybuilders got very less memory, but that's still better than zero. Now what they are capable of doing is, if your friend brings his friend, they'll probably allow him, and they'll also leave a 5 minute gap, as in once your friend leaves and till the next person comes in case if he's late. In between there should be no other person coming, because or else these guys memory is like very small. They'll forget that there was some person who has to come. So that is a small achievement, but a significant achievement. Now back propagation here as well. So all the neural networks are trained with back propagation only because the reason is it works, and this is the best thing that works to train a neural network. Scientists have figured out there's no other thing that is better than this. And in this case, back propagation through time, because time is really crucial here. You are also maintaining the sequence of it. So you will probably give less importance to the oldest information, and you will probably give more importance to the latest news. That is how our brains work as well. So we are always checking the latest news, but we don't really pay. Or we if I have to choose between an old newspaper and a new newspaper, I would pick the new one. So that is how these operate. And now, is everything sorted then? Probably not, because There is one problem called the vanishing gradient problem. It is basically you are operating on the gradients of weights or gradients of errors. So this is, you know, this is a sigmoid function that is involved in this, which has a range from 0 to 1. So basically it's like you are asking the bodybuilders to change the weight, and their lowest measurement of unit is probably 1 kg or zero point 0.5 kgs, and you have to tweak in 0.0024 kgs of weight. You cannot do it accurately, and hence you might, these dumb bodyguards might even, they'll be like, acha itna thoda weight hai to what difference would that make, and they will ignore, and a series of ignorance might lead to an utter chaos, and the kid might be super depressed, and the optimization will not happen. So that is the problem with vanishing gradients. After a point of continuous partial differentiation, the error becomes so small that it becomes almost insignificant. So you can't train a neural network in that way. And what is exploding gradient problems? When you use a ReLU function, which is again a function whose graph is weird. So this problem is again extreme. Like all problems lie in extremes. So this was approximating to zero before we wanted it to. The ReLU guy's problem is it explodes and it becomes greater than one, and it multiplies itself to become so large than the weight itself. So uh, it's like it's so dumb, like you are asking to remove 10 kgs from a 1 kg dumbbell, which is not possible. And what is the result is utter happiness and chaos. So that is still a problem for recurrent neural networks as well. So when then we come to, that is why we came to long term dependency and short term. This is again a different problem. Now, if you see in this, uh, Bob is eating an apple. So Bob and Apple are actually, very well maintained together by the neural network. But then if the sequence is increased or elongated, it starts to lose the context because, as I said, the memory is very less. So Bob likes apples. He's hungry and decided to have a snack. So now he's eating an apple. So he should be eating a snack, not apple. So that is the problem here. And this is again to our story analogy. Bodyguards are obstructing friend's friend who came late. So that is again very awkward and not something that should be happening. So that is where we come to LSTMs. So this is how an LSTM, long short-term memory cell, looks like. So this is basically very simple. It has three gatekeepers. It's very similar to RNN, but the inside structure of an RNN and LSTM is different. So what's different is it is a little bit more intelligent than those dumb guys. So you have three gatekeepers. One guy decides what to forget, one guy decides what to remember, and the third guy is busy in using these two informations and leads and predicting the next output. And that repeats itself in all these cells. So basically, this you can choose what to forget. So you will probably forget the useless information, and you can choose to remember what is important. Probably there's a person who has to come and he didn't come, he'll take at least 5 more minutes to come, so we'll have to remember him for more than 5 minutes. That is something very important. And this is the tanh function is again used to calculate these things. So remembering is done here, forgetting is done here, calculation is done here, and simple output is pushed on to the next cell, and the next cell repeats the same process in itself. And what's magical or smarter in this is you have a undisputed conveyor belt of context. So in this, there's this line which has a life of its own. So you can directly change the context and control the context here without depending on individual cells. So this one is a common track for everybody. So that makes these LSTMs smarter than RNNs. This is simply like as I said, this is an abstract explanation. Math is very simple, but for someone who's scared of math, this is the best way to understand. The forget gate, it decides what to forget, and the remembering gate, it decides what to remember. So these are the functions that are operated. This x is multiplication and plus is addition. So the update cell takes into consideration these two gatekeepers views, and then it performs updation, remembrance, and forgetfulness, and then it puts all those things, the new updated information, in this conveyor belt. What's magical here is you don't have to update every cell's conveyor belt. Because this is common, the updated news, the notification is sent to all the other cells. So now this has access to the latest, what needs to be remembered and what needs to be forgotten. So it doesn't have to do extra computations. So this becomes very easy while training the neural networks. You don't have to change the weights again and again, and the diminishing gradients problem can be overcome here. And this is the pass forward the context. So in this gate, after doing all this, it is also predicting the output of the cell and giving the output as a second input to the next cell. So that is how these things repeat, and this is a simple architecture. So you can see here, now what does this help, like what does this do? What this does is it gives more memory to your bodyguards, so they can remember more stuff, and probably they can operate efficiently. Bob and Alice are having lunch. Bob likes apples and Alice likes oranges. She is eating an orange. So this has been predicted by the neural machine translation. So even though the sentence was very long, it knew it had to forget Bob exists while predicting what Alice likes to eat. So if I was clear there. So that is how LSTMs help you in gaining the context, giving you more memory, and also giving you the power to edit your own memory on what to choose, what to remember, and what not to remember. And what's the result of this? A happy party finally. The bodyguards are like clever enough to allow all the guests and block all the unwanted guests. And the kid is happy, all the other kids are also happy, so that's a success. This is RNNs and their family. So RNNs come with RNNs are not like laws of physics. So they were a result of experimentation of different things. Everything in artificial intelligence and machine learning is an experimentation. So people can tweak things and they can come up with a different architecture as well. So there are a lot of architectures of RNNs. Bidirectional RNNs is something, each cell, instead of a one-way communication, cells can communicate with each other to perform better. And deep bidirectional architecture is also there, LSTMs and RNNs. Basically, deep means more capacity, but it also needs more training and more data. LSTMs that we just saw. Bidirectional LSTMs are something that are used in conversational agents and chatbots. Attention models is something, again, very lately introduced into the picture, and it is very efficient. So what attention model does is it also gets to choose the individual words where it has to give more importance to. So in a sentence, if somebody is talking about Times Square, it knows Times Square is important, so whatever he talks is revolving around Times Square, so it can hold the context for a longer time, better than LSTMs. And there's also some structure of pipelining and things where they interconnected every pipe off, like they did some random things to join these gatekeepers also and did something, they achieved results. So if you also want to experiment, you can. And let's come to applications part. So this is machine translation. These LSTMs are used in machine translation. So this is probably German, I guess. Now, like, this is translated. If you can see, the first observation we make is the input and output is not equal. So this is the superpower that the regular neural networks don't have. This can have any number of input and any number of output, and this is context based. So because this word came, it predicted this word, and because these two are there, its third prediction is based on these two, and because these three are there, it predicted the final prediction. And That's how the output is generated here. And this next application is text to handwriting. So definitely not for college assignments, but yeah, you can use. I'm gonna use this basically. So this again here, it's the same thing. Text is being converted into LSTM. With LSTMs, it's converted into machine or handwriting based. So how is it trained? Is again, it is being fed with the data, but it also knows how to find the context. So it knows how to make the cursive handwriting look a certain way instead of just printing. And this is the next application, which is cool enough: character level text generation. So what this does is you can give a book of your favorite author and let the machine understand. You can train it forever on that book and then see it predict according to what the book was. It can understand the context of the book basically. So this was fed with some philosophy book, and these were the results. Life is about the weather. Life is about the love of Mr. Mom. Life is about kids. Life is about an eating story. Life is about the truth now. So it's pretty philosophical because it was fed with philosophical books. This is the research paper. If you want to explore, you can. So this is again, and also you can stack LSTMs and recurrent neural networks on each other. That's some complex math, but you can do that. Just like how you had multiple bodyguards to make sure the kid is happy. A lot of times, too many chefs spoil the dish. So you might end up in a local minimum, and you might basically by heart the data instead of learning from it if you have too many layers. But if you have very less layers, that is very difficult to learn as well, so you'll have to find the sweet spot in between. This is the next application: image question answering. So you give an image that is unknown, and you ask what is the color of the cat. So first there's a CNN going and processing this image. So what it does is it says there's a cat wearing a hat probably and on a red, you know, mattress. And then you translate this question into the machine language that it understands. So what is the color of the cat? So it probably goes and gives you black. So what is the color of the couch? It's red. And the predictions, if you see, it's the predictions, and we use something called max pooling where we pick the thing with the highest probability. So here it's a gray, black, and black. Black is having the highest probability, so we pick it. Even here, red is having the highest probability, so we pick it. Likewise, these are the examples. Even this is another cool application: image caption generation. So now these neural networks can see an image because they also have the access to context as well as language. They can come up with their own interpretation of the image. So this was what AI came up with, or LSTMs now, because AI is something that people with no information use. Because we know what LSTMs are, we use that. So even this, first CNNs that identify the images, and then LSTMs doing their work. So generate, basically generation, wherever you have this generate term, it's basically all these LSTMs and RNNs and stuff. Even this video description generation. So a video is fed into it and it records every frame of it. It also observes every frame of it and gives you live, subtitles. A man is doing stunts on his bike. A herd of zebras are walking in a field. So if you see, these are LSTMs, and because they have access to the context, they are able to do this. And this is the paper. If you want to explore, you can. This is again one other cool application that I found out. You can add music to a silent video. So I couldn't play the video here, but you can watch a video. The neural network can watch a video. It knows what it is fed with data of how much pressure and force produces what kind of sounds. So now it has learned all that. Now it will observe this video and it will predict the sounds and it will generate the sounds. So all those old silent films can now be re-released on Netflix. And yeah, this is application number, I don't know, stock market prediction. Who wouldn't want to predict the stock markets, and who wouldn't want to forecast their company sales and stuff? So all these predictions, forecasting, stock market data is, again, as I said, very random, but there are patterns in that. So LSTMs will take care of those patterns. They will make effective predictions. In case of stock markets, bidirectional LSTMs with attention models work very well. So they might not give you 100% accurate results, but they are very good. If you see, the error is very small, so probably you one day you will find a very perfect stock market prediction thing. And I don't know what happens when everybody uses that to trade. Then somebody has to create another prediction which predicts these predictions. But as of now, this is the cool thing there. And self-driving cars. Even for self-driving cars, you have CNNs, you have neural networks that object detection things and all. But the prediction of which direction should I go next and where should I turn the steering wheel to is all dependent on the LSTMs and RNNs. So steering angle, speed, torque, etc., are fed into the data and fed into the RNN. It will then predict where I have to go. So if you, for example, take a ball and put it there, you cannot predict where the ball goes. So, but if you see a ball coming from left to right, you are likely to predict it will go towards right. Newton laws OP. And some more cool applications. Audio classification. You can classify audios, or like you can classify wind, rain, sunny day, and cold, snow, etc. All these things are amazing because these were something that was thought to be, this was something that was thought to be impossible or very sci-fi. But now, if you put all these things into one system, then the supercomputer is very close. Gender detection with audio input. Even this, your audio can be divided into segments and then analyzed on whether it is a male audio or female audio. So that can be done with a computer. That is a cool thing too. And probably the most effective thing for humanity, efficient diagnosis and medical reports. So, like basically, our moms have this inbuilt RNN. They'll predict if you get cold, you're most likely to get fever. So, do something so that you don't get fever. If you are on high fever, you're more likely to get jaundice or something else. So, our moms have those inbuilt RNNs. So, basically, these RNNs can be used in the medical systems to predict for complex diseases that nobody has any idea about or has very little idea about. So that might prevent people getting into some complex surgeries and stuff and whatnot. You can literally do anything that you wish to, because this is again of some free gyan from the recent book that I've read. So triangle inequality is so dumb. Fermat's light principle is so dumb. These guys became popular by pointing at something that is so dumb. This was what I used to think a lot of times. I would also have got into textbooks and stuff. But world operates on secrets, and every time there's a revelation of a secret, somebody becomes super rich and popular. And the secrets are on a spectrum where something is very obvious and something is very impossible. So time travel is probably something very impossible, and light goes in a straight line is something very obvious and it's already proven, and the achievable lies somewhere in the between. So all these things are the secrets that are somewhere in the achievable zone. And back then, nobody was looking at triangles inequality. So back then it was very novel and innovative. So Fermat's light principle was innovative because it was a secret back then. So even now there are a lot of secrets. You can explore all them with these neural networks and stuff. And coming to the coolest application, can you confirm, can you hear this music? Anybody? Well, you don't hear it. Uh, 1 second. Cha, there's no audio basically. I don't know what's wrong with this, but yeah, I did that. Uh, so- yeah, yeah. Now you'll probably get it. So that was probably the coolest application of these neural networks, because this music was a symphony that was left unfinished by Beethoven, and AI was able to, like, now we know it's RNN, it's not AI. So now we know what are these chemicals. It's not just a chemical. So these were able to finish this, and I couldn't believe this was generated by a simple neural network. So that is the peak that you can achieve, and people are still working on these. Transformers are the new trend right now, and yeah, that's and yeah, there are a lot of applications as well. So where can you see all this? And probably if you want to explore more, Stanford Online is a YouTube channel that has like so cool lectures that I binge watch now and then. MIT Open Courseware also has good lectures. There are cool people in AI too, like there's someone called Lex Friedman. He has like cool podcasts and stuff. And there's Coursera edX if you want MOOCs, and Medium blogs, etc. So there are a lot of resources, and even YouTube and GitHub, you can register into these things. Even Microsoft, Google, even they have their own courses. So if you want to explore, you can. And yeah, open to questions and feedback. Yeah, thank you. Yeah, a great session. Thanks, Akash. And yeah, just in case, just for the sake of it. So yeah, thank you, Slide. You can contact me if you want to, and I'll put this slide deck in the Discord channels. We'll also try to upload this video in YouTube. So if you like the analogy, just like Imran, you can share it with people and let them also understand neural networks without math. So I hope this session added some value. Okay. Thanks a lot for joining. If you guys can ask your doubts now, if you have, or give your feedback to we. I want to, like, we as a whole club want to become better at these presentations, so we want some honest feedback from you guys. uh, analogies made it pretty interesting. Yeah, thank you. That was the plan. We'll try coming up with better analogies next time so that we all can relate to. And yeah, like in future sessions, we'll probably do a hands-on, of one of these cool applications. Let's go through the code and stuff. Because once you understand the theoretical part of it, code is simply using the existing libraries and functions. So in the upcoming sessions, we can probably do something cool hands-on. And yeah, we still have 14 minutes. And we also have like other folks from DSC. So in case you have other doubts, you can ask. If there's no doubt, you guys can start leaving. Thank you for attending the session in the weekends. Yeah, Arey, I forgot to market my Twitter account.